Hey there, fellow learners. Welcome to this tutorial on Landau Notations. I'm Luay Abdul-Jabber, your TA for Applied Data Structures and Algorithms at UTD. Now today we're going to be delving into a topic that is essential for cracking the code on algorithm efficiency. That is Landau Notations. Let's break it down. Landau Notations are like language for algorithms, helping us understand their performance changes as input size grows. It's like road signs leading us through the complex landscape. Now let's take the first notation, the big O notation. Now let's imagine that we have this complex runtime for an algorithm. And now let's say that mathematically we were able to find an upper bound. What does an upper bound mean? It's basically the upper limit for how bad the algorithm would run. So let's say that we found the upper bound here to be g equals n. Then that means that the algorithm f, no matter how bad it would run, it would not run worse than linear time. So its worst case scenario is linear time, which is n. Conversely, big omega, on the other hand, is the opposite of big O. Let's say we have this complex algorithm running time, and let's say that we were able to find a lower bound for this algorithm mathematically. And let's say that that lower bound is n, which is linear time. So that tells us that no matter how good the algorithm f runs, it will never run better than linear time. So that's strictly the lower bound of this algorithm. Now, big theta is the sweet spot of both algorithms, represented by theta, or theta n. It's both upper and lower bounds. When an algorithm's runtime is theta n, it's a Goldilocks scenario. Not too fast, not too slow, just right. Now there are two other terms that are often confusing for some students. Little o and little omega. So if we look at little o, and let's say that we have this complex running time for the algorithm f. And let's say that we have this bound. It's not a strict bound. So we know that somehow mathematically that f will not go as bad as n, as linear time. So it will give us some idea of an upper limit, but it's not as strict as big O, because it will give us some room. So we will know that it will not know how bad f will run. It will not run as bad as linear time. It will be just a tad less than linear time. Similarly, for little omega, if we have this this line, then it would tell us that no matter how good this algorithm would run, we have some idea that it will not run as good as linear time, but it's close. We have some leeway here. So those are the 5 notations for Landau notations. Now, how do we think of Landau notations? Let's try to imagine that the Landau notations are different size boxes. The big O is an upper limit. The omega is the lower limit, and the big theta is just right, is the sweet spot. In a nutshell, Landau notations are backstage pass to decipher an algorithm's performance. They provide a universal language for describing how algorithms dance with input size changes. Remember, mastering Landau notations takes time, practice, and patience. Don't hesitate to ask any questions in our sessions and drop me an email. Let's keep exploring and conquering the algorithmic universe. Thanks for tuning in, and until next time, keep coding and keep learning.